Good morning. I'm Yuriy Shmaliy from the Universidad de Guanajuato, Mexico. And my talk will be about batch and recursive state estimation, namely about the trade-off in optimality and robustness. You know that state estimation can be provided in two equivalent forms, in the batch form and in recursive forms. But recursive forms are available only for white Gaussian noise, which leads to the Kalman filter, and for if we design an unbiased state estimator, that we can get some other recursion. Does it work? So I will introduce first the optimal state estimation technique in the optimal batch FIR filtering scheme, and also it is available in the finite infinite impulse response structure and the Kalman recursions. Then the optimal unbiased, which produce the maximum likelihood estimate by the FIR filter, then an unbiased FIR state estimator, and then we will go on with the robust state estimation techniques, namely with the robust H2 FIR filter, H infinity FIR filter, robust energy to peak FIR filter, and then some applications, some important applications, and finally I will summarize the results. This presentation will be mostly based on my recent book, Optimal and Robust State Estimation, Finite Impulse Response, FIR, and Kalman Approaches. And let's start with optimal state estimation. Louder?
Yeah.
I don't hear.
Stay very close.
Okay.
The motivation to design a batch state estimator instead of the Kalman filter was formulated many years ago by Yuriy. He said that a limited memory filter appears to be the only device for preventing divergence in the presence of unbounded perturbations in the system. That means that if we use only the recent history in our measurement, then the estimator will produce smaller errors. This is illustrated with this picture where we see that if we consider the history from 0 to the current point k, and the limited memory filter works from M to K, the Kalman filter from 0 to K, then the past errors do not affect the estimate. And so that we have the estimation error which diminishes with the Kalman filter probably for a long time, but the limited memory filter finishes the transient at this point. The discrete time state space model for the batch estimator can be designed in either in the backward Euler method-based state and observation equations, or using the forward Euler method. Here we show the backward Euler equations, which are the standard state space equations, this form, which we will further extend to the horizon of some points, so that if all the parameters and vectors and matrices are described correctly in this model, we can go on with the design of the more sophisticated but more robust batch state estimator. But first we need to use 4 general a priori and a posteriori measures, namely the a priori state estimate, the a priori state estimation error, the a posteriori state estimate, and the a posteriori error covariance matrix. The Kalman filter strategy implies that we start with some 0 point, specify the initial state and the initial error covariance. Also, we need to know all the noise covariance matrices, Q and R, and step by step from 0 to 1, 2, 3, and we go on until the current point K, so that the process is recursive, very fast, uh, uh, requires small memory, and produces the optimal estimate if the model is wide Gaussian. And the Kalman filter is the best estimator under such conditions, but the problem arises that when we do not know exactly the noise statistics, the output estimate appears to be either biased or noisy. The solution is the batch form, namely the batch FIR filtering form, and we will go on with this state estimator now. To design any FIR state estimator in the batch form, we need an extended state space model which can be created on the horizon from some point M to K on n past points by extending the original state space equations to the horizon of n capital points. And if in such a way we arrive at two new equations, these equations, where all the matrices and the vectors are in the block form. Now let's discuss how to create the optimal batch FAR filter, and then we will show that if you have the batch form, we can go to the Kalman recursions, and that was motivated by Kalman in his original paper that it is difficult to implement practically batch estimators if we are based on the impulse response of the estimator. Therefore, he proposed to use another approach, namely the recursive approach. But recursions do not answer the questions about the filter properties, so that we still do not know what is the impulse response of the Kalman filter, what is the transfer function. And if you do not know these general functions, we cannot say almost correctly about the Kalman filter performance. So let's go on with the optimal FIR filter. The gain for the optimal FIR filter based on the extended state space model can be derived if we solve the minimization problem, this one. Namely, we derive the gain for the optimal FIR filter by minimizing the trace of the error covariance matrix, applying the orthogonality condition, this condition, and from this condition we have two unbiasedness constraints, and finally, by describing all the necessary matrices and the noise covariances, we arrive at the optimal FIR filtering estimate that looks like this one. So this red box shows the estimate with the OFIR estimate. Here we have the general filter gain, the optimal gain, also the control signal, the control vector, and the gain is given by this relation, where three auxiliary matrices zeta 1, 2, and here are provided in the batch form in this way. The error covariance for this filter is given here. So we have here the matrix, which contains all the necessary information about the model and the filter. So we have here three residual matrices, B, W, and V, and using information about the noise statistics, we can supply the optimal FIR filtering estimate with the batch error covariance. What's interesting that when we convert this batch to the recursive form, the recursions appear to be the Kalman recursions. So we see here all the steps in the Kalman filter. But the Kalman filter, recalls that the Kalman filter starts from 0 and goes on until the current point. Here we, in the optimal FIR algorithm, we start with some past point M and go ahead using exactly the Kalman filter recursions. That's a very important point because next we should arrive at the conclusion that the Kalman filter is really an optimal estimator and not optimal unbiased as was thought before. We have here two intrinsic errors which are the property of the batch in the Kalman filter, so that the first problem arises when we do not know exactly the initial conditions, so that the Kalman filter starts from some wrong point and with a transient goes to the actual result, which corresponds to the correct initial point, this green, so that the blue transient may last probably for a long time, and that's a real problem for the Kalman filter if we are limited with the process, say, at this point. So the Kalman will produce very large result, very large error. Another problem is associated with errors in the noise covariances, so that if we are not able to describe correctly the noise covariances in the system and in the measurement, in this picture I show what's going on when we introduce some correction factor to both covariances, beta. Then if beta is exactly unity, then the Kalman filter stays at the optimal point. To the left and to the right, arrows grows up, and so that with beta less than unity, we see that the Kalman estimate becomes more noisy, and if beta exceeds unity, becomes more biased with a regular arrow. Now let's look at what's going on with the Kalman estimate and with the optimal FIR estimate if we embed unbiasedness in the structure. The estimator of this kind produces the maximum likelihood estimate, so that let's see what's going on. To derive the optimal unbiased FIR filter, we should minimize the uh, performance criteria, so we need to solve the optimization problem of this kind subjected to the unbiasedness constraint. So if we embed the unbiasedness into the derivation procedure, the output will give us the optimal unbiased FIR filter, which produces the maximum likelihood estimate. The cost function for this derivation includes the Lagrange multiplier, which must remove bias from the estimate. And if we will go this way, we arrive at the OUFIR filtering estimate of this form, and also to at the batch error covariance and two residual matrices which actually form the error covariance matrix. What's interesting that when we convert this batch estimate to the recursive form, the recursions appear to be not Kalman recursions. And the much more complex algorithm produces the estimate exactly in the same way like the batch form with the same values, but requires much more specifications and more recursive steps. But what's more important is that this algorithm is less accurate because the optimal means optimal. It's an optimal balance between the bias and random errors. But in this case, we follow, as we think, exactly the unbiasedness, the mean value of the process and also minimize the variance, but the output error appears to be larger than in the Kalman filter. And based on this result, we can say that the Kalman filter is not an unbiased estimator, as was previously thought. Let's now list the properties of state estimator in the batch form. The optimal FAI filter is the most general, the most other optimal estimators. It becomes optimal unbiased or maximum likelihood by embedding the unbiasedness. It converges to the unbiased FAI filter by ignoring noise. The batch optimal FAI estimate can be computed using Kalman recursions, but the batch optimal unbiased estimate can be computed using recursions different from Kalman recursion. The above means that the Kalman filter is optimal and not optimal unbiased. The problems. The optimal FAI filter requires all information about noise, model, and initial values. It is thus not protected against different kinds of errors and is not robust, naturally not robust. The optimal unbiased filter ignores the initial values. This is the advantage against the optimal estimate, but still requires information about noise and thus also a bit more robust than the optimal filter, but still not robust. Better robustness is offered by the unbiased FIR filter, and let's go on with this structure. So unbiased FIR state estimator. The general strategy of this filter implies that we use some past history from the point M to the point K, start with a short batch estimate, which is equal to the number of the states actually. So this is very short, and then iteratively approach the current point. So it is also the recursive estimator. But this estimator doesn't require neither the error covariances, not the initial value. And if the optimal horizon for this filter is given, that the unbiased FIR filter becomes practically blind. So it doesn't require any any characteristics. The result that can be made is that all transient in the UFAR filter are limited with the horizon length of n points and must be optimal in order to minimize the variance in this filter. And if n is defined imprecisely, the estimate will be either biased or noisy. The cost function for this filter is very simple. So we just track the mean value so that when we do not know the environment, the best way is to track the mean value of this environment so that the noise, the system and measurement noise in the structure can be of any distribution. The noise just must be zero mean. And the derivation leads us to the batch form in this structure, where the gain for the UFI filter appears also to be in the batch form. And we also have here the error covariance and two residual matrices describing the error covariance. But what's more interesting is that if you convert the UFI filter into the recursive form, that we arrive at a very short and simple recursions. They just require some optimal horizon of n optimal points to produce the estimate. And let's now compare the Kalman filter output with the UFI output in terms of the root mean square errors. That is only within the very narrow range from this point to this point that the Kalman filter outperforms the UFI filter. And why? Because this filter ignores the noise covariance, so that inherently is less accurate than the Kalman filter. But when we admit errors in the noise covariances, then the Kalman filter increases errors, and errors exceed the level of the UFI root mean square error. So the UFI filter appears to be very, very attractive for practical applications, especially for industrial applications when we do not know exactly the environment, we do not know the initial conditions. Often we do not know the covariance matrices, so that this is a uh, very tough conditions for any estimator. And the UFI filter works here much better than the Kalman filter. Let's now discuss how the length of the averaging horizon affects the UFIR estimate. Again, we see that when the averaging horizon is stay at the optimal point, the UFIR estimate ranges very, very close to the Kalman estimate, but still is less accurate. But when we reduce or increase the horizon with respect to the n optimal point, then the arrow grows up. But it is seen that in this example, for example, that when n ranges from 50 to 130, so it's about 30% of the estimation errors that the UFR filter works still very good, so that the 30% error can be accepted for practical applications. Properties of this filter. The UFR filter belongs to the class of Gauss squares. And so that it has respected advantages and disadvantages. The advantages are it doesn't require the noise statistics, initial error statistics, and the initial state. It is more robust than the optimal UFR filter and the Kalman filter under disturbances and uncertainties, whatever it means. And it is less sensitive to noise than the optimal batch filter and the Kalman filter. And the batch form of these filters has the computational complexity like O(n) to 2. So it's one annoying point for practical application. It requires time. But the iterative form of the filter has a complexity n, so that it is only n capital time operates slowly than the Kalman filter. But in the modern life, we use very effective computational methods so that using the parallel computing, the UFI filter can work as fast as the Kalman filter so that the computational complexity is 1. And to finish this part, let me say that the UFI filter appears to be the most robust state estimator among all other algorithms we know. But let's go on with the robust state estimation that especially was designed to increase the robustness. Our real life is full of perturbations, disturbances, uncertainties, and other unknown factors from the influence of which the estimator must be protected, and so that robustness. What actually is the problem? When we use any estimator, especially in harsh industrial conditions, under the known description of the model, then we face several sources of the problem. First of all, noise. Noise can be, theoretically, noise, we would like noise to be stationary, Gaussian, wide, but it is not in practice. Then noise can be impulsive, generated by different machines and like this. The model can be affected by uncertainties when we face some jumps in the velocity, phase, frequency. The initial values are often not known exactly, especially in robotics. When the robot stays at some position in the closed space, um, we start the process of to locate the robot. We do not know where is at the initial point. Temporal uncertainties also affect, like jumps, shocks, and other sources of errors. And finally, environmental and industrial effects that have different forms, various appearances, so that it is also the problem. Uh, how mismodeling occurs in the model? When we do not know exactly the process, when we are not sure that the model represents the process correctly, for example, we need to know only three states about the process, the distance, the velocity, and the acceleration. But it's only three states. In the process is much more complicated, and we ignore higher order states, then we see the problem with which is called mismodeling, or we face model errors. Of course, we need to do something to avoid this problem and to create some structure that is more protected against such effects than the Kalman and the Batch optimal filter. Filter sensitivity to sudden changes. There can be found a big number of temporal uncertainties in systems, including temperature, shocks, mechanical, and others. To characterize an estimator in terms of robustness against temporal uncertainties, we can suppose that a system is certain until time index n minus 1 and uncertain sudden changes at time index n. Then the response of the filter will show us the problem with robustness, like in this picture. So that if at this point we have some shock and the estimator, one estimator responds with this transient, and this one with this short, then this is more robust. The idea of design of robust filters is illustrated with this simple plot. So that let's suppose that we have some factor that affects the estimator and changes from n minimum to eta maximum. And let's tune the filter to this point. If we tune optimally, we go from point A to B. But when we then increase the factor, the error factor, then the estimation error grows up. On the other hand, if we will tune the filter to the maximum disturbance from the point C to the point G, and then the disturbance reduces, recall that it cannot be larger than the maximum, then we have a compensation effect. First, the filter produces larger error, then the disturbance diminishes, so that the resulting output error looks like this curve, so it is a very flat. And this is the main idea to design robust filters. It can be achieved in different ways, and let's consider several of those. The first, robust H2 batch filter. The main idea of the design of most of the known robust estimators is in the frequency domain, so that we just want to minimize the transfer function of the disturbance to error. And if you minimize this function and extract some useful information to design the filters, we expect that any disturbance in the input will go to the output as a minimum gain. The disturbance to error transfer function for the H2 filter is this one, and here we minimize the Frobenius norm, the trace of the Frobenius norm. The cost function is this one, and we face here three residual matrices which accumulate all the principal errors in the optimal estimator, namely the initial error, the system noise covariance, and the measurement noise covariance in the extended batch block forms. The homogeneous gain for the H2 filter after we pass all the derivation and skip the derivation procedure appears to be this one. And that's an important point that because we minimize the transfer function, the process must be stationary. And therefore, the filter also appears to be stationary. All the matrices so are time invariant. The a posteriori optimal H to FIR filter estimate is given with a traditional relation, so that we have the same function as before, and the error covariance matrix also has the same form, but the residual matrices are different, so that for different residual matrices, the filter gain becomes robust in the H to FIR filter sets. The a posteriori H2 optimal and biased FIR filter. We can also design this filter which produces a likelihood estimate, but this estimate is expected to be more robust relative to the standard form. So that if we follow consider the cost function and subject it to the unbiasedness condition, then the minimization of the trace of this matrix gives us the filter gain, the stationary filter gain, and the a posteriori H2 optimal unbiased FIR filter estimate appears to be in the standard form with the standard form of the error covariance, but with different residual matrices, which are functions of the new robust H2 optimal unbiased FIR filter gain. The properties of this filter. In wide Gaussian environments, the batch H2 FIR filter, the batch filter, is equivalent to the optimal FIR filter, and this filter is equivalent to the Kalman filter. So in wide Gaussian environment, we have all the solution equal. The recursive H2 filter is equivalent to the Kalman filter. The only difference is that the batch form doesn't have any restriction on the block error covariance matrix, so that it cannot be obligatorily diagonal as required by the Kalman filter, so that this filter theoretically appears to be more robust. Unlike the Kalman filter, the batch H2 filter can operate with full error covariance matrix, as I said before, so it's more robust in this sense. In non-wide Gaussian environments, the batch H2 FIR filter is more robust than the Kalman filter naturally. H infinity. The H infinity strategy implies that we must minimize the infinite norm of the arrow-to-arrow transfer function. It is equivalent to maximize the errors in the model and maximize the errors in the model, and then minimize the second norm of the output arrow with respect to the second norm of the disturbing arrows. From this strategy, the optimal cost appears to be in this form, and because the problem is mathematically intractable, the suboptimal cost practically gives us the H infinity gain of the batch filter, so that if we solve this problem with respect to some minimum value of the constant gamma, we obtain the H infinity FIR filter gain. The solution is given using the boundary trio lemma, so that to find this gain, we have to solve the linear matrix inequality in this form by minimizing gamma. And if you're able to do so, it's not so simple to solve, because one function is quadratic, and so that the LMI is not linear. But there is at least two possible ways how to solve this problem by creating an iterative form or modifying this inequality to have one additional variable, so that to become the LMI. The suboptimal H infinity filtering algorithm implies that we should solve the linear matrix inequality of this form with two variables with some restrictions. So I skip this part from the presentation because it's more complex. But if you describe all the matrices and all the vectors in this form, we finally arrive at the robust H2 infinity FIR filter gain. But we also can combine the properties of the H2 and H infinity filters and create a suboptimal H2 H infinity batch filtering algorithm by solving the minimization problem of this sort. And just one comment that we actually don't know how we have this gain because everything is inside the numerical procedure. There is no analytical solution, so that we finally just need to test the filter for some uh, basic result, for example, for the Kalman filter or for the optimal filter, or much better for the unbiased FIR filter that is most robust among other solutions, and compare uh, these algorithms to one another. The properties of H infinity FIR filter. The robust H infinity filter minimizes the maximum estimation error for the maximized disturbances. That's exactly what we need in practical applications. It gives more robust but less accurate estimates than the optimal estimator. Actually, this is the general uh, rule of thumb. When we increase the robustness, we do it at expense of optimality. So the optimal estimator is less robust and the robust estimator is less optimal. The H infinity filter is used when it is required to minimize the maximum errors in the estimate so that it is sort of maximum likelihood estimator. Another robust solution means that we would like to minimize the peak error at the output of the filter for the uh, energy of the disturbing error. The cost function for this filter, that is called energy to peak filter, is this one. So that here we solve the problem by minimizing uh, the output error in this form, and so that if you describe the H arrow, infinite norm of the output arrow in this way, then the cost function of the filter appears as the optimization problem when we maximize the energy of the disturbing arrow and minimize the peak value of the output arrow. Uh, the state space equation for this structure are this one, and we also use the energy to peak lemma to solve the problem. For this state space model, the lemma gives two conditions or constraints which are used to derive the gain for this filter. And the gain is derived if you minimize gamma subject to two constraints. These constraints are important and they are different from the H infinity filter, as you see. The properties of this filter. The robust energy to peak filter minimizes the maximum estimation error for the maximized energy of the disturbances and uncertainties of any kind. So we need to take care that we have described it correctly, all the influences in the model, and then we can arrive at the robust gain. It gives more robust but less accurate estimates, as I said before, than the optimal estimator. The L2 to L infinity filter is used when it is required to minimize the maximum estimation error in the estimate for the maximized error energy. When it is required to minimize the peak estimation error to the maximized peak disturbance, there is another filter, L1, but I do not consider this structure. It is very similar, but I do not consider it in this presentation. So let's go on with several applications. This first picture shows the effects from one of the practical results shows that the effect of robust tracking of the moving vehicle. If you tune the filter to the regular initial point when the disturbance factor is considered to be zero, and so that the arrow grows up, produces large arrow, but when we tune the filter to the maximum disturbance, it stays at this point, and then the disturbance appears to be smaller. Then the output arrow appears to be flat. It is, of course, produces larger arrow than the optimal tuning, but it is robust in all this area. Recall that robustness means low sensitivity to disturbance factors. In this picture, we see how the robust UFIR filter fits the temperature tracking. It's one day measurement of the periodicity of one day, and we see that the red, the robust fitting is much better than the Kalman filter. That just cannot be tuned into this mode because we do not know the conditions for the Kalman filter to be tuned correctly. This experiment with mobile robots was conducted in one paper, and we see that the robust extended for nonlinear models UFIR filter operates better. They state that it operates better, is more robust and more accurate than the Kalman filter under the real operation conditions. In this picture, we see how the accuracy can be improved in multi-MEMS inertial measurement unit by using the iterative UFIR robust filter, so that we see that unlike other filtering solutions, the UFIR filter is able to produce a minimum possible error in this structure. I have many other applications, but let's finish with this interesting result, which shows the experiment conducted by China in space. It's adaptive controlled moving robot in space applications. Again, they said that among other filtering solutions, the robust UFIR filter, recall that it is the most robust among other linear filters, gives the most accurate results. In summary, the optimal FIR state estimator, the batch approach, is the most general for linear models. It becomes unbiased, optimal unbiased by embedding the unbiasedness, and becomes unbiased by ignoring noise. The Kalman algorithm solves the optimal FIR filter and is thus optimal. The optimal unbiased FIR filter gives the maximum likelihood estimate and has recursive forms different from Kalman recursions. The UFIR estimate is computed by unique iterative algorithm, very simple algorithm, is the most robust among other state estimators. Methods of robust FIR state estimation are used when the system operates under disturbances and certain as other errors. And among many other solutions, the most interesting solutions are achieved in the frequency domain, so through the transfer function, so the model must be stationary. The H2 filter is equivalent to the Kalman filter in wide Gaussian environment and is robust otherwise. The H infinity filter minimizes the energy arrow. The generalized H2 filter minimizes the energy to peak arrow. The L1 filter minimizes the peak to peak arrow, and all these filters give most robust results than the optimal solutions. Among all the solutions, the UFIR filter demonstrates the highest robustness, and this filter is most attractive for, say, harsh industrial applications. That's actually all. Thank you very much.